Lecture 27, Stress. In most textbooks, stress is defined as force divided by area. Because force is a vector and area is a scalar, stress defined in this way is also a vector. For that reason, we call it the stress vector, or more correctly, a traction vector. Notice that when we talk about tractions, it is always with reference to a particular plane. The official unit of stress is the Pascal, which is Newton over square meters. In the Earth, most stresses are much bigger than a Pascal, so we often use the unit megapascal, which is 1 million pascals. 1 megapascal is equal to 10 bars and almost 10 atmospheres, and it is also equal to 145 pounds per square inch. In the Earth, compression is more common. Therefore, in geology, compressional stress is positive, and tensional stress is negative. In engineering, it is the opposite: tensional stress is positive, and compressional stress is negative. A stress vector on a plane can be divided into a normal stress perpendicular to the plane, and a shear stress parallel to the plane. Furthermore, in this example, the shear stress can be divided into shear stress parallel to the first axis, and shear stress parallel to the second axis of the coordinate system. We can extend this idea to 3 dimensions to look at stress at a single point in the rock, which is represented by a very small cube with faces perpendicular to the axes of the coordinate system. In 3 dimensions, there are 9 tractions which define the state of stress at a point. There is a convention for the subscripts of the different tractions. The first subscript identifies the plane by indicating the axis which is perpendicular to it, and the second subscript shows which axis the traction vector is parallel to. For example, sigma 2,1 is the traction acting on the plane whose normal is axis 2, and it is parallel to axis 1. Thus, the components of the stress are the normal and shear stresses on planes perpendicular to the axes of the coordinate system. Normal stresses have equal subscripts, whereas shear stresses have unequal subscripts. The 9 tractions can be written in matrix form. Sigma I, J, is the stress tensor. Notice that if the cube is in equilibrium so that it does not rotate, sigma 1, 2 should be equal to sigma 2, 1, sigma 1, 3 to sigma 3, 1, and sigma 2, 3 to sigma 3, 2. In other words, sigma I, J, is equal to sigma J, I. Thus, there are only 6 independent components of the stress tensor. This means that the stress tensor is a symmetric tensor. We now have a better definition for stress. Traction is force divided by area. Stress is a symmetric tensor defined by 6 tractions. Stress relates 2 vectors, the traction on a plane, P, and the unit vector describing the orientation of the pole to the plane, N. This is known as Cauchy's law, and it is written in index notation on the right side of the slide. Like any symmetric tensor, the stress tensor can be expressed in terms of its principal axes, where only the diagonal of the corresponding matrix has non-zero values. The principal stresses are the tractions which comprise the stress tensor when the coordinate system has the principal axis orientation. Sigma 1 is the maximum principal stress, sigma 2 is the intermediate principal stress, and sigma 3 is the minimum principal stress. These principal stresses define a stress ellipsoid. This ellipsoid and its orientation tell us everything about the state of stress at a given point in the rock volume where stress is homogeneous. Now let's look at some important terms. The mean stress is just the average of the 3 principal stresses. Because the sum of the diagonal elements is a stress invariant, we do not need to know what the principal stresses are to calculate the mean stress, it is just the sum of the diagonal elements divided by 3. With the concept of the mean stress, we can divide the stress tensor into 2 components as indicated by this equation. The first component is the isotropic part or the mean stress. This part is responsible for the type of deformation mechanism as well as dilation. The second component is the deviatoric stress, it is what actually produces the distortion of the body. Note that for the deviatoric stress, the maximum stress is always positive, that is compressional, and the minimum stress is always negative, that is tensional. Finally, the differential stress is the difference between the maximum and minimum principal stresses. Notice that the deviatoric stress and the differential stress are two different things. People often mix these two. To learn more about this topic, read Chapter 4 of Fossen and do his e-learning module on stress. And answer these questions.